Welcome to all. This is part 3 of design of shear reinforcement for beams by working stress method. For the group it is class 32C. Now, before I start, see, in part 1 and part 2, I considered design of shear reinforcement using only vertical stirrups. Means shear reinforcement consists of only vertical stirrups. That is the most popular case practically. Any building you go nowadays, you can always see vertical stirrups. What extra we are considering, that cranked bars, you will not see everywhere. Olden days, they used to crank the bars. But nowadays, that is not practiced. But usually in bridges all, they do it. So anyway, theoretically, it is possible. So therefore, I am taking up the case now. So remember, this part 3 and part 4 is meant for design of shear reinforcement when cranked bars are available for resisting shear. Now, when cranked bars are available for resisting shear, how it is possible, or how, when you consider a cross section, how the cranked bars will come, that all I will not tell here, because I am not taking up the full subject. In the group I told, see, in the group I clearly told where you get the cranked bars for resisting shear. See, suppose some cranked bar comes this way. When you take cross section, suppose the cranked bar is here. If you take cross section here, you can see the cranked bar on the upper side. If I take cross section here, little down. So cranked bars will be available somewhere in between. That is not discussed here, because this is only the strength part. Cranked bars are available for resisting shear. So, design of shear reinforcement for beams in the form of vertical stirrups. Remember, now also vertical stirrups are there. Last time also I told vertical stirrups, but vertical stirrups, when, see the color, I am to understand correctly, I am using green color for cranked bars. When the bent up bars, see, IS code used the word bent up bars. But usually people use the word cranked bars. So I decided to use the word cranked bars more, not bent up bars. Bent up bars or cranked bars. Easy. Cranked bars, class, are available to resist shear. Okay, now, see, class means IS code has told bent up bars. We will refer it as cranked bars. Now, one important aspect, I will tell now only. Those who want to study thoroughly and understand, they should correctly go through part 1 and part 2. What is tau V, what is tau C maximum, what is tau C, what is the spacing of shear reinforcement. See that formula. If you remember, see this formula. This all explained there. I will not repeat. If you do not thoroughly study those two parts, there is no point, first of all, to come to this class. Just a waste of time. So, requirement from your side. When I do the numericals part, I will tell all those extra notes or principles I told there, I wrote there. I will not tell here. I will not write here. I will tell here, but I will ask you, write it down later. So, without dedication, it is not possible to learn. Remember, I always insist it. Those who want to learn from me, they should follow what instructions I give. So, part 1 and part 2, you have to thoroughly study, then come to part 3. Okay, now see. Data, as usual, B, D, AST provided for cross-section considered. Concrete and steel grade. Shear force for cross-section V. This is same data, you can write. You can round off this way here. Round off this way and write. This is the same data we required for earlier case when the shear reinforcement was in the form of only vertical stirrups. But now, and extra data, also details of the cranked bars available for resisting shear for cross section considered. Class. Details of the bars means what is the number of bars available, what is the diameter of the bar that you require, how many cranked bars are there. Where it comes not required. So when I solve the problem later, I will tell maybe 2 cranked bars are available. Somebody may question, where is it? It is available. When you go to this case, you will be knowing it. Suppose you go for a design of a bridges, there you can see the cranked bar if they crank it. Or when the cranking is done, you can see it. So here, cranked bars are available because I am not covering the complete RCC here. But in the group I told correctly, how it is, with the sketches I told, how cranked bars are available. Okay, now, note, important note, this is what I am telling. Note means everything is same as last time. Only extra is this green color. So from beginning up to end, it will be repetition. So therefore, everything earlier, note, everything same, but along with everything same, but along, see, I write earlier, note, everything told earlier is same, everything told earlier will be same here also, but along with the vertical stirrups, cranked bars are there. That's the only thing extra. And therefore, see, vertical stirrup is a shear reinforcement. Cranked bar also shear reinforcement. I have simply used the word ASV and VS. They did not differentiate between vertical stirrups and cranked bars. They told ASV is the cross-sectional area of the shear reinforcement. VS is the shear strength of shear reinforcement. Earlier cases, both are only for vertical stirrups. Therefore, we simply wrote ASV and VS. Because why? We know it. It is for stirrup. But here, for vertical stirrups also ASV, for cranked bars also ASV, for vertical stirrup also VS, for cranked bars also VS. So what I will do is, IS code has given that way, we will use suffix. We will use a suffix here to differentiate with suffix. What I will do is, whenever we consider vertical stirrup, see, stirrup, ST, I will use the suffix ST. So, if you remove the suffix ST, it will become your previous case. And wherever cranked bar is there, I will use green color CR. I told you here. Also, wherever suffix ST for vertical stirrups, CR for cranked bars. This is to differentiate between the two. IS code has not given it. And also, everything same. Tau V, tau C maximum, tau C, and also later spacing SV for what SV for vertical stirrups. Everything same. So therefore, I need not explain too much. Already explained too much here. Okay. Go to procedure. All you have to do is follow the procedure. Procedure. Find nominal shear stress for cross section tau V equal to V by BD. Even though IS code called nominal, I am telling shear stress due to shear force V. Okay. This is same as last time. From table 24 of IS code, get tau C maximum. Waves means write what is told last time. Maximum limit for tau V or shear stress, or it is the maximum limit, or shear stress for the cross section should never exceed tau C maximum. It is the maximum limit for shear stress. Okay. Compare tau V with tau C maximum, same as last time. Tau V should not, see, so far cranked bar has not come. Tau V should not exceed tau C maximum for safety. Okay, now, if tau V exceeds tau C maximum, cross section to be redesigned. Over. Now, one thing forgotten here. See, you write here. Now, continue the procedure when tau V is less than or equal to tau C maximum. I forgot, right? I told last time also, if tau V is more than tau C maximum, you have redesigned. So now, tau C max. Now, procedure continued when tau V is not more than tau C maximum. Okay, continue. Get tau C. I should not waste time. based on PT. This all I told last time. 100 AST by BD, table 23, get tau C. Compare tau V with tau C. Case 1, tau V less than tau C. Shear reinforcement is not required to be designed. Class. If shear reinforcement is not required to be designed, cranked bar is of no use. Even if cranked bar is there, it's a dead one. See, cranked bar will come into picture only when shear reinforcement is required. So you can write here. So in case you get tau V less than or equal tau C, then it becomes ordinary question. The cranked bar will not be considered. It will not be, it is not there. It is there, still not there. Okay, class. However, provide nominal or minimum at maximum permissible spacing as per IS code. I have given last time 1, 300, 2, 0.75D, 3. I told the expression for you. Okay, now. Case 2, tau V is more than tau C. Then shear reinforcement is required. Why? Shear stress exceeds the limit of concrete. How much is the shear stress? It is more than how much shear stress concrete alone can resist. So shear reinforcement is required to be designed. Decide number of legs and diameter of vertical stirrups. Someone will tell, sir, crank, wait. I told you same as stirrups. As we should see, last time I wrote, let us provide 2 leg, 8 or etc. Decide number of legs and diameter for vertical stirrups. Note, class. Up to here, same as last time. Cranked bar will not come. We do not know what is cranked bar up now. But now onwards, right here, up to here. But now onwards, cranked bar will come. So again note, class. Stirrup and cranked bar, both are shear reinforcement. So now, to understand correctly, we will use suffix ST for vertical stirrups, CR for cranked bars. Okay. Now, IS code formula for spacing. See, SV equal to, this is sigma SV, ASVD by VS. I told last time only sigma SV, sigma ST, but sigma SV should not be taken more than 230, all same as last time. And ASV is cross-sectional area of legs of stirrups. VS is shear force to be resisted by vertical stirrups. But now what happens is, cranked bar is there. So this ASV, I will put ST. Nodi, this is ST. This also ST, ST, ST. What we call last time as VS and ASV, because last time cranked bars are not there. Now it will become for stirrup ST over. Now remember, VS equal to V minus VC last time. Money matter, I will tell you next time. So that when I do a numerical, I will explain the money matter. But here, shear force, we want what? Earlier all, this VS is shear force to be resisted by stirrups. But cranked bar was not there. So we simply wrote VS. But this time, we require VS ST equal to V minus VC. What is the shear force? Subtract strength of concrete and also subtract VS, one more VS. This is for cranked bar. It is so simple. Last time, from the shear force, subtract how much shear force concrete alone can resist. Remaining for stirrups. Now, how much shear force is there? Subtract how much shear force concrete alone can resist. Also subtract how much shear force your cranked bar can resist. Okay, now. So, VC is as usual, same shear strength of concrete, tau CBD, no change. Now, so new term, VSCR is shear strength of cranked bars. Now this requires, now this is a new for you, new. So I will thoroughly explain. 1 minute. I will prepare the board. Everything I will remove now. Remember, you can take a screenshot of this one. Then when I come back, I'll start from here only. See, everything is required. You should not do this way. You should continue in the same book. Then compare. So now, ready to introduce cranked bar. 1 minute. I'll fully clean it. See, remember, by this time, you know the value of V, you know the value of VC, it's the black color. You know the value of V, you know the value of VC, you know the value of V. Right here, V is known, VC known, even formula for spacing also is known. Earlier it was ASV and VS, now it is ASV ST and VS ST extra. That's all. I'll continue procedure. This all I will not explain once again. I'll start fresh from here. I have to clean the board and write. We will continue. I told VSST equal to V minus VC minus VSCR. You know V, you know VC. VSCR I told. Okay, now refer IS code. VSCR equal to sigma SV ASV of CR into sin alpha. Now, sigma ASV CR is cross-sectional area of the cranked bars. Pi by 4 of diameter square into number of cranked bars. You should write it. If you want, write here. Those who want, write here. Pi by 4 of diameter square into number of cranked bars available for resisting shear. Sigma SV, same condition, not to be taken more than 230. Alpha is the angle at which between the cranked bar and axis of beam, or it is popularly called as angle of cranking. Everybody knows it. Most popular angle is 45 degrees. If not given, take 45 degrees. Okay, then. Now, but this one. But now remember, this is expression for strength. You should write here. This is expression for strength of cranked bar. But IS code has got a condition. I will write as per IS code. As per IS code, shear strength of cranked bars shall not be taken more than half of shear strength of total shear reinforcement. Total shear reinforcement means you should not take strength of cranked bars more than half of shear strength of cranked bar plus shear strength of stirrup. Because stirrup and cranked bar both are shear reinforcement. If you add both the strength, how much strength will come? This cranked bar strength should not be taken more than half. Now, that is, see, this is the statement given in IS code. So many people will not understand that one. I will tell. Now I will give you mathematical version of this one. See, this is the condition. Next class I will write the condition. Then I will tell that actually means this VSCR should not be taken more than half of V minus VC over. This is conclusion of that limitation. If you use logic, you can easily understand. See, if you use logic, no one told me all these things. If you correctly understand the logic, directly you can tell this answer. But I know, in the beginning, more than 99% people will have difficulty. However, during numerical example, this will be explained in detail. And also, some example which you will understand will be given. You know what is that example. What else other than money matter? Some money matter I will tell. Then all in my offline class I have seen. Suddenly they tell, sir, fully clear, sir. Why? Because money matter. So this is my responsibility of clearing this one. Okay, now, first what you do, substitute in this equation. Get the value of VSCR. Then apply the condition and decide what VSCR is to be considered. Okay, now, how? Some will ask, How, sir? Find this value, apply the condition, and what VSCR should, and decide what is the value of VSCR you have to consider. How? Later in example I will tell this. Then come back. Later in example I will tell crystal clear. Then what you do is you come back to procedure and write here. See, you write here. See where? Then apply the condition and decide VSCR to be considered right here. That is this way. You write it here. When the example I will tell you, those who are serious, come back to procedure, leave some space here. Leave some space here, right here. Okay, over. Now we got the value of VSCR. Substituting, get VSST. Shear force to be resisted by stirrups. Earlier this was only VS, now VSST. Over. Okay, now get VSST. Then, actually I write here. Then substituting, already there, in this equation, already everything explained now, nothing pending here. Substituting in this equation. Oh, just 2 minutes more. Okay. Here. This all problem will be eliminated when I start. If I use a smart board, but it will take some time. Substituting in this equation, substitute here, substituting here, substituting in this expression. Substitute, not substituting. Then substitute in this expression and get SV. That is spacing for vertical stirrups. Vertical stirrups. Again I told you last time, remember, strength based. This I will not explain now. Means later you should not give a spacing more than this one. Okay, then lastly, same as last time, referring to IS code, get maximum permissible spacing. See, little earlier I wrote MPS, spacing for vertical stirrups. Vertical stirrups, that is 300 millimeter to 0.75D. Actually, 0.75D has got technical meaning. It is not a number. Some people will tell, why 0.75D? IS code. No, it has got reason about the shear crack. Okay, leave it now. Third one, ASV into 0.87 Fy divided by 0.4B. Condition, Fy not to be taken more than 415 Newton per mm square. Then, among these three values, consider the least value, that is maximum permissible spacing. Lastly, then compare SV you got, SV based on strength, SV based on strength with maximum permissible spacing, and decide spacing of vertical stirrups. Decide spacing of vertical stirrups. Over. Procedure over. Any difficulty is there, confusion is there, you go through once, leave it. Comes to example. In example, I will explain everything once again. All the logic, etc. I will tell. Then do one thing. Again come back to a procedure sheet and write everything there. That is the maximum I can do, because this is, I am uploading in the YouTube so that it is useful for general public. But all these are actually part of my regular course running for my RCC group. So many things. See, 0.75D, I crystal clear explained for them. If I tell all those things here, there will be no end for here. So that you have to understand. Okay, now this is class 3. Class 4 will be same working stress method, concluding part numerical example for this one. Then 1, 2, 3, 4. Same 1, 2, 3, 4 will be repeated 5, 6, 7, 8. Instead of working stress method, it will be limit state method. That time you will be knowing how much similarity is there. See, limit state method. VUSCR 0.87 FY. VUSCR, VUC, VUSCR, VUS. This is all same. Okay. That I will explain. I will take after finishing part 4. Immediately by tomorrow, you will get part 4 also. So working stress method gives you good idea. And one more thing, if you understand working stress method, same pattern for limit state. So preserve this one for future reference. Thank you.